etc., etc. So chapter 3. In chapter 2, we learned how to address the difference quotient, how to apply or determine limits of functions, and then we put these two concepts together, and what did we create? What is the limit of the difference quotient? How do we call it? Exactly. Finally, in chapter 3, we're going to talk about differentiation rules. I also posted your WebAssign homework for test 1. If you increase your grade, let me know and I'll look again. But for now, the grades are posted. Okay, differentiation rules, and let's start with one function that is very important. I know nobody cares about it, nobody really likes it, but we would like to determine the derivative of this. And this time, just one time, let's use the definition. Can anyone tell us how to determine f prime of x for the square root of x? Did we determine the square root of x, the derivative of the square root of x before? I don't remember doing it, but you have a fresh brain. We did? With the definition?
I thought we did, at least.
Okay.
Maybe your lexes
From before?
Yeah.
Okay, let's just do it, just this time. You'll see why in a minute. Okay, can anyone dictate the definition?
Is this the limit is h approaching 0?
Excellent, of course. Of course.
F of x plus h minus f of x.
Of course. Excellent, thank you, Mari. Okay, so then I plug it in. And this is the square root of x plus h minus the square root of x divided by h. And of course, I'm going to plug it in. And what do I get when I plug it in? As expected, I get
Plug in 0.
What do I get?
0 over h.
0 over 0. When I plug in 0, I get the square root of x minus the square root of x, which is 0 over 0. It's 0 over 0, correct? Agreed?
Yep.
Okay, perfect. Is the difference the limit of the difference quotient? It has to be 0 over 0. Okay, so then how do we proceed? What do we have to do here? Of course. So we'll multiply by the square root of x plus h plus the square root of x divided by the square root of x plus h plus the square root of x. What is the factor that you expect to remove from the top as well as from the denominator?
Square root of x.
Very good. Awesome. H is the problem. H creates 0 over 0. Exactly. If I have here h approaches 4, and I get 0 over 0, then x minus 4, h minus 4 is the problem. If I have h approaches negative 3, and I get 0 over 0, then h plus 3 is the problem. But since I have h approaches 0, I know the problem is h. So I'm hoping to remove h. The denominator is clear. And can anyone give us the numerator?
X plus h minus.
Very good, thank you very much. So these two go away. I'm hoping that we see that the two h's go away. And I can already write, so this piece goes away with this piece. One at the top and one here. So can anyone give us the final answer?
1 over square root of 2, or no, 2 over square root of x.
That's it. Thank you very much. So moving forward, we know this. And this is carved in stone. We have to remember it. I don't like saying that, but since we proved it, we have to remember it. We're going to use it a lot. Any questions? Is this clear? Okay. So that's one rule that we have to remember. Here's the second one. Let's look at f of x equals x squared. And you could say, well, you're still torturing us with the definition. You haven't shown us any differentiation rules. I will in a minute. So let's apply the definition on this one as well. So f prime of x equals, and we're going to apply the definition one more time when we get to trig functions. And then we can put it to rest. So this is
X plus h squared.
limit as h approaches 0. Indeed, x plus h squared minus x squared divided by h. Obviously, when I plug in 0, what should I get?
0, 0.
Correct, it is true. Now, we have two options. We either expand x plus h to the second power, or we factor, because this is a squared minus b squared. Which one? It's up to you. Both are fine. I just want to make a decision, though. Okay, can anyone expand this for us?
X squared plus 2xh.
Excellent. And of course, as we expected, the terms without h go away. Obviously, what happens next is we factor out what from the numerator? Of course. That will cancel or simplify, if you want better, the denominator. And what is left in parentheses?
2x plus h.
And now we're ready. The answer is? Very good. So then x squared, the derivative, the function that gives the instantaneous rate of change of function x squared at any point where the function is differentiable, but polynomial functions are continuous and differentiable everywhere, is 2x. So in general, can anyone suggest a formula for any power on x?
I think I see.
Yes.
Drop the,
Yes.
exponent
Times-
directed it by.
Exactly. So this is the power rule. The power can be a fraction. The power can be negative. So let's look at an example. Let's say x to negative 3 prime. How will you differentiate this?
Negative 3x to the negative.
So we do not like negative exponents. So we're going to continue and simplify it to negative 3 over x to the 4th. And now, I would like us to differentiate, just in case we forgot, the square root of x. And you can say again, yes. Just bear with me for 1 second. I want to differentiate the square root of x using the power rule. Can anyone tell us what is the power on x?
X squared.
Very good. So please bring down the power. Please subtract 1 from the power.
1 half x and negative 1.
I have 50 cents,
So
but I owe you $1.
1
I still owe you
still a half.
1/2. Very good. As expected. We knew the answer because we determined the derivative of the square root of x using the definition. So we knew that. Any questions on this? Is this okay? Okay. Here's another rule. It comes from the limit laws. Let's say we have a function plus another function prime, or let's say we subtract. Can anyone give us the idea? How do we determine the answer? The derivative is a limit, so it's the same rule.
You buy both.
F prime plus G prime, or minus. The derivative of a sum is the sum of derivatives. The limit of a sum of functions is the sum of the limits. The limit of a difference of two functions is the difference of the limits. Same thing. What about a constant multiplied by a function, prime? Same rule from before, the same limit law. C is coming out as a factor. It cannot be differentiated. There is no need. So, like it comes in front of the limit, it's C times the limit, or C times F prime. Okay, so we know how to differentiate the square root of x. We know how to use the power rule. We know what happens when we add or subtract functions, when we have a sum of two functions or a difference of two functions, and we need to differentiate that to find the derivative. We know how to apply or differentiate a constant times a function. Say it again.
I was wondering if I was in the way.
And now I would like to talk about e to the x. Just one this time, one more time with the definition, so we see what's happening here, and then we'll look at the applications.
Same as before.
Yes, please.
X minus 1. What is that?
See how my markers are getting messed up?
You have to put the letter first.
Yeah, sure. Very good. Limit as age approaches 0.
E to the power of x plus 8.
Thank you very much. Excellent. Great job. Perfect. So now, what do you think I'm going to do next? Well, of course, I plug in 0, it's 0 by 0, obviously. So what will be the next step? There is nothing I can do to this. There is nothing I can do to this. So my only chance is this. What can I do to it? Let me give you the idea. A raised to m plus n is a raised to m times a raised to n, and vice versa. Multiply two exponential notations with the same base. I copy the base, add the exponents. So I want to break this up. How do I do that?
X plus.
Careful.
Oh, sorry, times.
Yes, exactly. E to the x times e to the h minus e to the x divided by h. Excellent. Okay, what next? What do you think I'm going to do next? I know you know. Careful.
Or,
If I cancel something from the top, I have to cancel with something from the denominator, but there is no e to the x in the denominator. So what is my only choice here?
Factor out e to the x.
Excellent. Thank you, Paige. So limit, stage approaches 0, e to the x, e to the h minus 1 divided by h. Got it. And now you could say, well, this particular example does not fit your two-step procedure. The first step, all terms without h must go away. They do, because this is a constant. It does not depend on h. This depends on h. This depends on h. This is like a constant, like 5. So I'm allowed to put it in front. It does not depend on anything. And now you can say, well, but you can simplify the h in the denominator. And then I have to say yes. We don't know how yet. There is a procedure, but I cannot show it to you right now. So we still have to determine this limit. So for now, I do have available a numerical possibility. So let's look at the numerical possibility. Please. Okay. So let's plug it in. in y equals, in parentheses, e raised to x, of course, I can put h in there, minus 1, and divide by x. So this is e to the h minus 1 over h. Where am I interested in determining this limit? Near what?
0.
Very good. Now let's see what we get. Go to second and table. I didn't mean that, I meant this, because I knew I had to change the setting again. Okay, so I'm going to plug in negative 0.1, then negative 0.01. And I got tired of it. I'm going to go from the other side. 0.01, 0.001, 0.1. So this limit of e to the x minus 1 over x is 1. So then, if this equals 1, what does the derivative of e to the x equal to? It's the nicest function on the planet. Its derivative is the function itself. Yep. So we proved it. We didn't prove it algebraically or with the theorem, which we will later. But now we know what this is. So the derivative of e to the x is e to the x. Okay, so let's look at a few applications. Let's say 35 on page 182. And we have y equals x to the 4th plus 2e to the x. And they are giving us a point 0, 2. So it says find equations of the tangent line and normal line to the curve at the given point. I am not going to graph the function. I just want to give the idea. Assuming that this is the function, f of x or y, assuming that this is the point 0, 2, the problem is asking us to determine the equation of this line, which is the tangent at that point. And they also want us to determine the equation of the normal line, which is the perpendicular line to the tangent at that point. So this is normal line. So they want us to determine this equation and this equation. So let's start with the tangent. What do I have to do first in order to determine the equation of the tangent? Or first of all, determining the equation of a line, what do I need? I have a point, which happens to be 0, b, which is the y-intercept. So y equals mx plus b is good enough. I don't need to go back to y minus y1 equals the slope times x minus x1, which is the point slope one. Because I noticed that the point that was given to us is the y-intercept. But, so I have the 2. This is 2, but I don't have the slope. How do I determine the slope? We know this from the previous chapter. This time we are going to be able to determine the slope without using the definition of the derivative. So how do I determine the slope? Let's find y prime. Can anyone give us y prime?
So it'd be 4x to the third
Plus a constant times a function. Prime is the constant times, that's it. We will evaluate this at x equals 0. Why x equals 0? Because that's the point we are given when x is 0. So what is the answer when x is 0?
2.
That's it. So then the slope is 2. Can anyone give us the equation of the tangent line to the point, to the graph of function y, or f of x, at 0, comma 2. What is the equation of the tangent?
Y minus y1, right?
Say it again.
Is that when you use y minus y1?
Y equals 2x plus 2. Y equals 2x plus 2 is the equation of the tangent at 0, comma 2. Good. Now we want to determine the equation of the normal line at the same point. What do we know about two perpendicular lines? What do we know about the relationship between the two slopes of two perpendicular lines? What do we know?
The inverse.
Say it again.
The opposite reciprocal.
The negative reciprocal of the other one. So perfect. Or what I like to remember it is m1 times m2 equals -1. If the slope of the tangent line is 2, what could be the slope of the normal line so that the product is -1? Or just say the negative multiplicative inverse is the same thing. So what will you say if you don't use this? What will you say? What is the slope of the normal line? The negative multiplicative inverse of 2 is? That's it. So all I have to do now, write y equals mx plus b, where b is still 2, and the slope this time is -1/2. So y equals -1/2 x plus 2 is the equation of the normal line. At 0, comma 2. Any questions? Ready for the next problem? Questions here? Is this okay? Okay, so here's the next one. 67 on 183. We're given a function f of x squared plus 1 for x less than 1, and x plus 1 for x greater or equal to 1. So we are asked, is this function differentiable at 1? Sketch the graph of f and f prime. So we're given a function. What type of function is this? How do we call it? Piecewise defined function. Excellent. Okay, so do you think this function is differentiable at 1? Let me rephrase that. Maybe I should answer it. We talked about it, but just once. A function is not differentiable in 3 situations. When it's not continuous, when it has a vertical tangent, or when it has a cusp or a corner. You can say 4. Cusp, corner, vertical tangent, or not continuous. If a function is continuous, is it guaranteed to be differentiable? I just said no. By giving 3 examples in which the function was continuous, but it has a vertical tangent, a cusp, or a corner. So if the function is continuous, it's not guaranteed to be differentiable. But is the reverse or the converse true? Absolutely. If a function is differentiable, it must be continuous. No cusps, no corners, and no vertical tangents. But it must be continuous. Is that clear? Okay. So first of all, I have to make sure that the function is what at 1? Continuous at 1. Okay. So let's test continuity at 1. Because, why am I testing continuity? I'm asked whether it's differentiable at 1. I don't know. But if it's not continuous at 1, I have the answer. But if it's continuous at 1, Is that sufficient to conclude that it's differentiable at 1? No, because you could have a vertical tangent or a cusp or a corner. Okay, so what is the definition of continuity at the point?
And,
Continuity at x equals 1.
and f of x for the left exit.
Limit. I didn't hear. I'm sorry. Forgive me. X approaches 1 from the left.
Is equal to
Yes.
as x approaching 1 from the right is equal to
F of, not f of x.
1 rather.
Exactly. Perfect. Awesome. Thank you. Good. So this is which one?
Probably the first one, so x squared.
Very good. And this is clear. It's x plus 1. So what does this equal to?
2.
Excellent. What does this equal to?
2.
And what does this equal to?
2.
What do we conclude about this function? Is it continuous? We have not discussed differentiability yet. Is it continuous at 1?
Yes.
It is continuous at 1. So it's continuous everywhere because this is a continuous function, it's polynomial. This is a continuous function, it's polynomial. We show that it's continuous at 1, so this function is continuous everywhere. Agreed? Okay, so now let's talk about differentiability. I have no idea. When is a function differentiable? When it has one tangent. Okay, so let's talk about this for a second. What if I have this situation? This function is continuous. But is it differentiable at this point? No, because it has a tangent here, which is negative, and another tangent here, which is positive. So this is a corner. So then let's go back to f of x and find f prime. For less than 1, because we know it's differentiable at when x is less than 1, and for greater than 1, I have not discussed differentiability at 1. But I know that this will always be differentiable to the left of 1. This will always be differentiable to the right of 1. Okay, so let's differentiate, not with the definition. We're taking a break from that. So with differentiation rules, and what I did not mention, let's talk about it right now. What is the derivative of any constant?
0.
Perfect, because a constant does not change, does not have a rate of change. Perfect. So can you please tell me what is the derivative of x squared plus 1? Excellent. What is the derivative of x plus 1? 1. That's the slope of the line. Perfect. Okay. Now we're going to graph both the function and its derivative. Obviously a major point is where? Or major x value, or a very important, crucial x value here.
1.
Exactly. So 0 has to be in the table and 1 has to be in the table for both. From the notation of x less than 1, remember we are using negative infinity to 1 in case you are using my method, and 1 to infinity for the function. So a parenthesis opening to the left and a bracket opening to the right, right exactly under 1, and they are touching. Okay, so on this side, I know we have a quadratic function, and on this side we have a linear function. So let's plug in. I'm going to plug in -1, 0, and 1. So when you plug in -1 in x squared plus 1, what do you get?
Still 2. Yeah, still 2.
2. Excellent. When we plug in 0, we get?
1.
Good. When we plug in 1, we get?
2.
Good. On the other side, when we plug in 1, we get?
2.
And when we plug in 2, we get?
3.
Good. So it's very clear, even from the table, that this function is continuous at 2. There is no open point and full point. There is only one point that is full. Okay, perfect. So please make sure that you graph both the function and its derivative one under the other. So make sure you have enough room. And the y-axis have to look like they are the same. Of course, they're not the same, but they're the same vertical line. Okay, so I will plot -1, 2. I will plot 0, 1. I will plot 1, 2, but open. And this is the quadratic function. And now the linear function, but it starts at 1, 2, so I have to fill this in. And then 2, 3. And this is the graph of f. Now we're doing the same thing for the derivative. It's just that the derivative to the left-hand side of 1 is 2x, and to the right-hand side of 1 is 1. So here, 2x, and here is 1. And don't forget parentheses. I don't know if I'm going to put something in there, so for now I leave it blank. But this is nothing else but negative infinity to 1, and this is nothing else but 1 to infinity. So I have to use parentheses. This parenthesis facing this way, this parenthesis facing right, and I don't have anything inside yet. And I cannot make them touch. We've used these graphs a lot already. These tables, I meant to say. Okay, so I'm going to plug in some numbers. Let's say 0. What do I get? Good. And let's say I plug in 1. What do I get? Good. Let's say I plug in 1 here and I get? Good. Let's say I plug in 2 and what do I get? Good. Excellent. So now I'm going to graph the derivative. So at 0 is 0. At 1 is 2. Done with that piece. And now 1, 1, 2, 1. So this is the function called f prime. And now let's analyze. Does f prime, which is a limit, this is also open, both of them are open, but it's not very clear. So remember, f prime is a limit. Okay, so does f prime exist at 1? No. The left-hand side has a slope of 2, the right-hand side has a slope of 1. So this one has a slope of 2, and this side has a slope of 1. So I can now guarantee the derivative does not exist at 1. What do we conclude about the function? If the derivative is not continuous at that point, in other words, then the function is not differentiable at 1. Because remember, at this point, the limit of the difference quotient has to be one number. The limit from the right is 1. The limit from the left is 2 when age approaches 0 of the difference quotient, which is f prime. Okay, so maybe we should write this if we didn't already. That continuity does not imply differentiability. Does not imply differentiability. But the other way, yes. If a function is differentiable at a point, it must be continuous. If a function is differentiable everywhere on its domain, it must be continuous everywhere on its domain. Okay, let's look at motion. The equation of motion of a particle is this. I would copy it as s of t because it's a function of t, where s is in meters and t is in seconds. Find the velocity and acceleration as functions of t and find the acceleration after 1 second. Okay. So let's copy the function. So this is problem 48 on page 182. And we have s of t, which is t to the fourth minus 2t cubed plus t squared and minus t. Distance is in meters and time in seconds. Find the velocity and acceleration as function of t. Okay, so this is a distance function. The velocity is obviously, as we know, the rate of change of distance with respect to time. Can anyone give us S prime?
4t to the power of 3 minus 6t to the chip plus 2t minus 1.
Excellent. Thank you, Payne. Very good. Everyone understands this step? It's okay if you say no. Okay, so the power rule says that we have to bring down the power and subtract 1 from the power. Is that clear? Then we have to bring down the power. We have to multiply it by 2 and we subtract 1 from the power. And then we bring down the power and we subtract 1 from the power. And when we differentiate negative x or negative t, we get negative 1. Better? Very good. Okay, so that's the velocity. The measurement unit, remember, of any rate of change has or will be a ratio of 2 measurement units. So it's the rate of change of distance with respect to time. So the measurement unit for velocity will be meters per second. Now, the acceleration is the derivative of the velocity or the second derivative of the distance. So the acceleration now will be the rate of change of speed or velocity with respect to time. That's why it's meters per second, but that is meters per second squared. So velocity is measured in meters per second, acceleration in meters per second squared, and let's determine the second derivative of the first derivative, the rate of change of the first derivative, which is the velocity. Can anyone dictate? 12t squared minus 12t and plus. Good. Finally, here we are asked to determine the acceleration after 1 second. All I have to do is just plug it in and find a of 1. And it will be in meters per second squared, the rate of change of velocity with respect to time. So when I plug in 1, I get 2 meters per second squared. Questions? Okay, let's take a look at one more and then we can continue, I hope, unless you want to work on more problems. 63. Let's read it together on 183. And let's see what we're asked to do. Find a second degree polynomial p such that p evaluated at 2 is 5, p prime evaluated at 2 is 3, and p double prime evaluated at 2 is 2. So let's copy this down. So p of 2 is 5, p prime of 2 is 3, and p double prime of 2 is 2. So in this situation, we're asked to find a unique polynomial. You will not find 2 polynomials that fulfill these 3 conditions. There is a unique polynomial that fulfills these 3 conditions. But first, we have to think about the most general polynomial, degree 2. Can anyone give us the most general polynomial degree 2? Okay, I got it. Please.
X squared.
That is not the most general. This is the nicest and the simplest possible quadratic. We want the most general one. This we like, and we use this for transformations a lot. But we want the most general one.
X squared plus bx plus c.
Of course, this is the most general polynomial degree 2. A, B, and C can be any real number. However, A cannot be 0. Why? Why A cannot be 0? I say A, B, and C can be anything, but A cannot be 0. How come? A, B, and C can be any real number, but A cannot be 0. How come? Because if A is 0, it's no longer quadratic. It's linear. It's just bx plus c. Okay, perfect. Good. So how many conditions, how many equations we have to write, and how many unknowns we have? In order to fully define this polynomial, what do we need to find? What are we looking for? We want to fully define this polynomial. How do I fully define it? What should I find in order to tell you this is it and no other? What do I need to find? Of course, A, B, and C. I don't have A, I don't have B, and I don't have C. Once I get these 3 numbers, then the polynomial, quadratic polynomial, is fully defined. No one can find another. Good. So then how many equations we have to write? Of course, 3 variables, 3 equations. Perfect. Good. So can anyone first determine P prime for us? Because we have to use it. And then P double prime. Or the first derivative of P and second derivative of polynomial P. Okay, P of X. Can anyone give us P prime?
2ax
Excellent.
plus, which one ends up being constant? I'm just not sure which would be. X would just be 2, or will we, is that too far ahead?
We're here. We have to differentiate this. What do we get? What if they were 2x? What would you get?
Not a 2.
Good, but it's not 2, it's bx. Excellent. It's just b. Perfect. Great job. The second derivative now. We are differentiating the first derivative.
2a.
Very good. 2a. Good. So now we have 3 equations to write. P of 2 is 5. Can anyone tell us how to write P of 2 is 5? And then P prime of 2 is 3, and P double prime of 2 is 2. I copied them here so I don't look at that page anymore. Okay? So please dictate. P of 2 equals 5. What do I write?
A2 squared plus B2.
Good. So 4a plus very good. Plus, very good, equals? Excellent. That's the first equation. Great job. How do I find the second equation, please? Excellent. Equals?
3.
Excellent. Final equation, please.
2a equals 2.
Excellent. Great job. Where do you think I'm going to start? And no, I'm not lazy, but that's where we have to start. Correct. Good. So how much is A? Good. Please plug it in here. Replace it by 1 and tell me B. So,
Oh, wait, no. I just -1.
perfect. And now replace A and B in the first equation and give me C. So that would be 4 minus 2 plus C equals 5. And how much is C? Indeed. Great job. So can anyone dictate the unique polynomial, completely fully defined by these coefficients, A, B, and C? There's no other polynomial that fulfills the given conditions. Good. I'm ready. Yes?
X squared
Of course.
minus b
Minus x.
plus
That's it. This is the only polynomial that fulfills the given conditions. Great job. Great job. Any questions on this? Is it clear what we did? So please remember, this is the most general polynomial, degree 2. Can you, for example, give me the most general polynomial, degree 3?
b ax to the third plus bx squared plus c x plus d.
That's it. That's the most general polynomial, degree 4. Degree 3, and so on and so forth. Degree 4, and is that clear? Okay. Now this is really the nicest, and we use it in transformations. But we cannot use this in transformations unless we complete the square. Okay, ready? Like before, please always remember to bring a lot of questions from WebAssign. Not everyone is doing the work in WebAssign as you should, so please, you will learn a lot from those examples. And you saw a lot of these questions that we had on the test. I just simply copied them from there. I'm sure you recognize them. Okay, so section 3.2. Product and quotient rules. I present these two rules slightly differently than in the book. Feel free to use the method you like. The reason it's a matter of habit, of course. The reason I use the sequence that I'm going to show you in a minute is because I think that this is the structure should be 1, 2, 1, 2 instead of 1, 2 plus 2, 1. But it doesn't matter. Whatever you get used to, it's fine. So when we are differentiating a product or of two functions, or we are differentiating a quotient of two functions, or a ratio of two functions, this is not what you would expect. And in case you're wondering how to prove these rules, there is an easy method. I just don't want to go through it. If you can read it here. There's an easy method in which geometrically it's very easy to show that if you increase the width and increase the length, it's very easy from here to see how we get to the differentiate the product. And the same thing, the ratio, very similar. So if you'd like to look at it, just look at it. It's on page 185. But for now, I'm just going to give you a direct result. It's the first function prime times the second one plus the first times the second prime. Your book presents this part as g prime times f. It's up to you. It's the same thing. It's f times g prime or g prime times f is the same thing. I just prefer 1, 2, the first function times the second function prime, because I say that a lot in my lectures. So kind of gives structure, but it's fine if you prefer the method in the book. So when we differentiate a product, first times the second, first function times the second function, it's a sum of two products. First function prime times the second plus the first times the second prime. This is the basis of integration by parts in Calc 2. This formula, or rule if you want. Okay, the same thing with the quotient. It's just that the quotient has a ratio. I'm not going to write it here because it crashes with that g prime f, so I don't want to confuse you. So f over g prime, the numerator is very similar. F prime times g, but minus f times g prime, so it's very similar to the product rule. And the denominator is not differentiated but squared. Again, if you like this particular structure, you don't have to. You will not ever hurt my feelings if you use a different method. So it's 1 prime times 2 minus 1 times 2 prime divided by 2 squared. So now I would like to practice these two with some examples that we will choose. You will choose, I will choose, it's up to you. Okay. Then I would like to look at applications in which we don't really have the function. I'll enlarge this in a moment for you to pick. And also read from a graph. Okay? So let's start with some examples. So we should start with a quotient. We should also start with the product. I mean, we should also look at the product. Either this or this, it doesn't matter, and then a quotient. And then we can look at applications. So see the way they present it in your text. They start even the quotient. So see, first, second, second, first. So they're not only twisting it. It's your fault you did that. I watched you. So it's not only, so they write the second term as the first function prime times the second. And then, so they also do this and also twist the product, in my opinion. But it's up to you, right? So they do use the same formula for the, no, they don't even use the same formula for the numerator. Now they twist it in a different way. Because it makes sense. This is the correct order. So it's confusing. That's my opinion. But you use the method you like. As long as you're getting the right answer, I don't care. Okay, so let's choose a ratio and the product. You only have 3 seconds to choose. 1, 2, 3. 14. You lost your chances. You waived the right to choose. The right to choose is within a time limit of 3 seconds. This is not a good color. Okay. So 14 on page 189. And we have y equals x plus 1 divided by x squared. No, I think it's x cubed. Yeah, it's x cubed. So x cubed plus x minus 2. We see a quotient,